Hello there, this is Jude Socrates. Welcome to video number 11 in my series for multivariable calculus, Math 5C at Pasadena City College. So in our last video, we learned how to set up and compute double integrals over general regions. So in this video, and actually in some of the coming videos, we are going to continue doing just that, setting up a double integral and then computing it. So practice, practice, practice. Today, what we're going to see is how to use a double integral to find the volume of a solid. So we're going to look at a couple of tetrahedrons and we're going to find their volumes. So we're going to go to Scientific Notebook now and look at our first example. All right, this is going to be a quick stop because we're just going to look at the problem. We have these four vertices, the origin, 2, 0, 0, 0, 4, 0, and 0, 0, 3. And by the way, you can also follow along on page 18 of our PDF. So we are now going to GeoGebra and we're going to plot these points and draw our tetrahedron. All right, I have gone ahead and plotted our 4 points over here. There they are. So what we're going to do now is we're going to connect the vertices to complete our tetrahedron. So you'll see that, I believe we've done this. Click on segment and let's start at the origin. So let's make A to B, all right. And then let's do A to C. There we go. Default color is black. A to D right there. And then let's plot the other sides. So how about from B to C and from B to D. There we go. And finally from D to C. Okay, there we go. So tetrahedron, we have 4 vertices and we have 4 sides. Okay, we have lots of edges, 1, 2, 3, 4, 5, 6 edges, but let's swivel around over here, take it for a spin. There's our beautiful tetrahedron and we're going to find its volume. Okay, you could probably go on the internet and look for a formula for volume of a tetrahedron, and I'll actually talk about that a little bit later on. Okay, so to find the volume of this tetrahedron, we need to interpret the volume as a double integral. Okay, so what does that mean? Well, we need a domain. Okay, so to get the domain, we'll need the top view. All right, so there is our x-axis in red and our y-axis in green. Okay, so we just got a right triangle, obviously, right? And of course, 2 points collapse there. And in fact, the entire edge from A to D collapses to a single point when we look at this tetrahedron from above. Okay, so there you go. So therefore, this will be our domain of integration. Okay, so this triangle with sides 2 along the x and 4 along the y. Who is the function that we are going to integrate? Okay, so that's where interpreting the integral as a volume is going to be important. Okay, so remember that we are drawing boxes, okay, with a little base, a little rectangle here, and the height is the value of the function, of a function, at some point in that rectangle, maybe the midpoint. Okay, so it looks like, I hope you would agree, that the function that we need is this plane. Okay, the plane which contains the triangle made of the 3 non-zero vertices, non-origin vertices. Okay, so we need to find the equation of this plane. Okay, if you're over here, the height will be right there on the plane until your head touches the plane over there. Okay, So for this, I hope you remember from our first PDF, Thinking in Three Dimensions, we can find the intercepts form of the equation of this plane because they're right here. The intercepts are 2, 4, and 3. So of course, this is the reason why I chose these particular vertices. Okay, it's easy to find the equation of that plane. Okay, so we have two things we need to do. We need to create our domain using this right triangle, and we need to find the equation of the plane formed by these 3 points. Okay, that will help us to set up the double integral, and after that it's downhill. All we have to do is apply Fubini's theorem to compute that double integral. So let's go back to scientific notebook. All right, so you know what? Let's do the easy part first. Easy part. The equation of the plane containing the triangle. So that triangle was these 3 points. Okay, so we're going to use the intercepts form. So that is x over 2 plus y over 4 equals I'm sorry, not yet, plus z over 3 equals 1. Okay, so the function we want is from z. Okay, so how do we get z? Isolate z, bring x and y to the right, and then multiply everything by 3. So when we do that, bring x and y to the right, minus, and minus y over 4. And then we multiply that whole thing by 3. Okay, so this is the function that we are going to integrate. This will be our f of x, y. Okay, sorry, it looks a little bit weird. All right, of course we can simplify this a little bit if we want to. Just distribute that. We'll do it in our setup. Okay, so now the domain of integration is the right triangle on the plane with vertices. So we have these 3 points, but they're only on the xy plane. Okay, so it's just 0, 0, and then 2, 0, and 0, 4. Okay, from the top view, there is no z. Z is just 0. Okay, however, what we need is a type 1 or a type 2 setup. Okay, so you saw the right triangle. It is both a type 1 and a type 2. It's a simple domain. So as a type 1, okay, so what do we have? X is going from 0 to 2. So x is from 0 to 2, and y is between 0, the bottom, and the hypotenuse. Okay, so let's just put that down. Y is between 0 and hypotenuse. Okay. Let's just abbreviate. Okay, but what is the equation of the hypotenuse? It passes through these 2 points. Oh, wait a minute. Those are intercepts again. All right, so use the intercepts form in 2 dimensions. Okay, so even simpler. It's going to be exactly this, but there's no z. Okay, it's just x over 2 plus y over 4 equals 1. Okay, so from there, we get y. This will be our g of x. Will be, isolate y, so bring x over to the other side, 1 minus x over 2, and then multiply the whole thing by 4. Okay, so definitely that is worth simplifying, distributing 4 minus 2x. Okay, so now we get our hypotenuse, that's our g of x. Okay, so we are ready now to set up our double integral. All right, so everything that we need is in this screen. So I'm gonna just paste my template for the outer integral. X is going from 0 to 2. Lower limit of 0, upper limit of 2. Okay, and we have dx on the outside. So we have dy on the inside, and we'll have our function. And I guess I'll just copy this and turn x into y. Y goes from 0, so that's already correct. And then the upper limit is 4 minus 2x. So great, we have 4 minus 2x. Okay, and the function that we are integrating is up here, our f of xy. It is this, okay? So, should we distribute the 3? I don't think so, because we have our properties that 3 can just go out of the integral. Okay, so there we go. That is our setup to find the volume of this tetrahedron. If you like, you can pause the video and try to compute this on your own. Okay, you know exactly what to do. We're going to integrate with respect to y, and then plug in the endpoints, and then integrate with respect to x on the outer integral until we finally get an answer. Okay, so yeah, go ahead and pause the video, and then when we come back, we'll show you the solution. I hope we get the same answer. All right, so let's do this. I'll copy this down here, and let's just take that 3 all the way out. Okay, so that is our integrand, and now we get to integrate with respect to y. So copy. This turns into y minus x y minus y squared divided by 2. That's going to be over 8. Okay, so we've done the integration, and what we need to do next is plug in the endpoints. All right, so for that, I need this, and I will paste this thing inside. Okay, there we go. That's my evaluate symbol. So we are going from y equals 0. This goes now over here, and we're going up to y equals 4 minus 2x, that whole thing. Okay, there we go. So nope, just up to there. Right, so we are going to plug in the upper limits and the lower limits. So lower limit, we get all zeros, so thank you very much. We only have to worry about the upper limit. So replace y with 4 minus 2x everywhere. See, we don't need parentheses there, but we need that over there, and definitely over there. Okay, so the rest is, well, I shouldn't say the rest, but at this point, we need to do some algebra or a u substitution, okay? So the way I see it, okay, the way I see it, we should distribute this x. That part is not too difficult. However, this one is really up to you, okay? If you feel okay expanding this square and then dividing by 8, that's fine, okay? We can do that. Or we can keep it together and then just do a u substitution. U can be this, and then you can solve for du minus 2 dx. And then for dx, don't forget to change the dx for this integral. You'll get minus 1/2 du. Okay, so you know what? Let's do that. So maybe that's what you did actually. But if that was not what you did, then yeah, how about at this point, pause the video again and then see if you can perform the integration of this term using just a u substitution. Okay, and maybe you'll prefer to do that the next time this problem comes around, this kind of problem. Okay, let's do that. All right, so let's simplify the first two terms. We will get 4 minus 2x, and then we'll get 4x over 2, so that's 2x minus another 2x, and then you're going to get plus x times 2x squared over 2, so that's plus x squared. So we're going to get x squared minus 4x plus 4. Oh, that's interesting. That's interesting. This is x minus 2 quantity squared. Ooh, a little surprise there. Does that help us? Oh, wait, check it out. Look at this. I did not recognize that right away. Maybe you did. That term we can rewrite as factor out the 2, so you will get a 2 squared, 4, but you will be left with 2 minus x squared. All right, see what I did there? Take out 2, so you're left with 2 minus x. 2 squared is 4, so that goes out. Okay, but 2 minus x squared and x minus 2 squared are exactly the same, aren't they? So this is actually 1/2, 4 over 8, 1/2 x minus 2 squared. Ooh, the plot thickens. Okay, so what does that mean? So this whole thing that we have inside the integral, our integrand, is exactly, okay, we said that the first 2 simplifies to this, and then we subtract this. Okay, so this minus half of it, you're left with half of it. So, yeah, that's all we got. Okay, so therefore, continuing, okay, let's copy where we left off over here. So continuing, this becomes, we got a 3 over 2. Okay, so let's take that out. 3 over 2 integral x from 0 to 2 of x minus 2 squared. Aha! Dx. Okay, and again, you can expand that out and then integrate term by term, or use a u substitution. Let's do it the smart way. U will be x minus 2, so dx equals du. Okay, very nice. Du equals dx, dx equals du. But now, when x equals, let's do that on the next line. And let's scroll up a little bit with some space. When x equals 0, u equals negative 2. And when x equals 2, u equals 0. Okay, so maybe that part looks a little bit weird. So let's bring that here. And we get, this will be 3/2. And then we now have an integral with u limits. Okay, so let's label it anyway. 0 became negative 2. And 2 became 0. Okay, and then we have u squared du. Okay, so that's fine. And let's see. Okay, So what do we get? Ah, yeah. Okay, so we're fine. We're fine. No worries. I was worried there for a little bit. Probably saw it on my face. So we're ready to integrate. We will get 3 halves u cubed over 3. Okay, and we are integrating from -2 to 0. Okay, so this is the part that I got worried about because we don't want a negative answer. Okay, but my worries were for naught, for nothing, because when we plug in the endpoints, we will just get 0 minus, whoops, so that should now be 6. Okay, or go ahead and simplify it to 1/2. Okay, so when we plug in the endpoints, okay, 0 will stay 0, but the -2 will become -2 cubed, minus -2 cubed. Okay, so that will turn out to be plus. Okay, so that's a -8. 8 divided by 2, ooh, we're going to get 4. Okay, so that's our final answer. The volume of this tetrahedron is 4 units. Okay, 4 cubic units. All right, so let's go back to our PDF for a little bit. All right, so here we are on page 18, and we have this example, which is similar. Okay, we just have different values for the 3 intercepts, but of course it's solved in exactly the same way. All right, you look at the top view, and you solve for the plane containing the 3 non-origin vertices, and solving for z, that's the function that we integrate. And then you do the intercepts form, and that's the upper limit of your integral. Okay, so this looks very similar to what we just did. Okay, but I'm taking you here because we can, of course, make this general. Ooh. So you can have a tetrahedron where you have the origin, and you have 3 vertices, 1 on each of the axes. And let's assume, of course, that they are all positive numbers. So we're on the first octant. Okay. So this is the general intercepts form. And then you can also do the same thing for the hypotenuse of our domain. And if you do all of that, repeat the process, and it will be in your exercises. This is the volume that you're going to get. 1/6, 1/6 of ABC. Easy as 1, 2, 3. So does that fit? Does that check what we got? Okay, we got 4 cubic units, but our vertices were 2, 4, and 3. Okay, 2 times 4 times 3, 24 divided by 6. That gives you 4. Okay, and of course the smart way to do it is 2 and 3 cancel with the 6. Okay, so you're left with the vertex at I believe 0, 4, 0. So that's the 4. Okay, so our next example will generalize this volume problem. Okay, so for the tetrahedron, we said, okay, the height of your little boxes will be up to the inclined plane formed by those 3 vertices. Okay, the bottom of those boxes are all on the xy plane. Okay, so that's why that's the height of the box. Okay, but what if you actually have 2 surfaces? Okay, so hopefully this will remind you of something that you did in basic calculus. Okay, and in fact we saw it when we talked about type 1 and type 2 regions. Okay, in a type 1 region, you have x going from A to B, and then y bounded below by some g1 of x and above by some g2 of x. Okay, so it's the same thing for solids if you want to find the volume. Okay, you might have the same common domain, okay, but you have 2 surfaces. Both of them are above that common domain, okay? But you have a surface which is entirely below a second surface, and you want to find the volume of the solid which is between them, having that shared common footprint. Okay, so what we're going to do is we're going to modify our example, and we're going to find the volume of another tetrahedron, not this one though. Okay, I'm going to give you a very different example. Okay, we're back. So I'm keeping the origin and the 0, 4, 0. Okay, but these are two really different points. They're not intercepts at all. Okay, so we have 3, 2, 1 and 3, 2, 5. And I'm sure you heard, oh, they both share 3, 2. It's just the z coordinate, which is different. We have 1 and 5. Okay, so let's go to GeoGebra and let's make this tetrahedron. All right, so again, to save us some time, I plotted the 4 points over here. And yeah, if we move around, yeah, of course, C and D are definitely not on any of the axes. They're not even on the XY plane. Okay, they're just floating around in space. Okay, but they do share the same X and Y coordinates. Okay, so there they are, right on top of each other. Okay, so let us draw the tetrahedron. Okay. Okay, so connect the edges, the vertices rather, segments. Okay, this should sound familiar. A to B, and then A to C, and then B to C. Okay, so let's stop right there, and let's see what we have so far. Ooh, so that is obviously the bottom of our tetrahedron. Okay, it is not on the XY plane. Okay, so let's form the rest. Okay, so we'll have an edge from A to B. Okay, there you are. All right, and then D to C. Oops, okay, did you get stuck? D to C. Just acting up on me. So there's D to C, and we have one more D to B. All right, right there. So now we have completed our tetrahedron. Okay, so yeah, it looks like it's kind of floating around in space. Yes, the bottom is not on the XY plane. Okay, however, when we look at the top view, okay, so we got a nice triangle there. It's not a right triangle anymore. Okay, so is it even a simple region? Is it both type 1 and type 2? Okay, so remember we had that nice right triangle before, that the 2 and the 4. Okay, and all we had to do was solve for the hypotenuse of that triangle. Okay, but now we have this triangle. Okay, so think about that. Let's mentally scan that triangle with both vertical arrows and horizontal arrows. Okay, so vertical arrows, that's a type 1 test. Ooh, it looks like we pass. Okay, so our x is going from 0 to 3. Our y is going from this lower function, y is a function of x, and this upper function, y as a function of x. Okay, so this is a good time to draw this picture on a sheet of paper, because we're going, of course, to set up the integral and compute it. Okay, so this is our domain. We have the origin, and this vertex is at 3, 2. Why 3, 2? Because that's the common footprint of these two vertices. They're on top of each other over the point 3, 2 on the xy plane. And then this is our vertex V, B at 4. Okay, so we have 4 over there. Okay, so we need to find the equation of this line segment, solve for y. The equation of this line segment, solve for y. Again, practicing setting up a double integral. Okay, however, we also need our surface above and our surface below. Okay, so the surface above is the plane which contains the triangle A, B, and D. Okay, so that is our upper function. Okay, so I'm going to write that down. The upper is A, B, D. Okay, and the lower is A, B, and C. Okay, very good. So that's the information that we need from GeoGebra. Okay, who is the function above? Who is the function below? So we have f minus g in our setup. Okay, and we need the equations for our domain. X is going from 0 to 3, and then y is going from this lower line segment to this upper line segment. All right, back to Scientific Notebook. Whoops, I just realized that I didn't mention the type 2 scan. What if you did horizontal arrows? It's not going to work out as nicely because you're going to exit on the lower line segment for arrows up to 3, 2. And then once you go above that, you're going to exit on the upper line segment. So you're going to need 2 integrals for a type 2. So now let's take the type 1. Okay, set up the double integral as a type 1. Okay, so x we said is going from 0 to 3. You hear the birds in the yard? And okay, so y is from the line segment, let's just call them L1 to L2. Okay, scoot over. You trained yesterday, so the birds must be very happy. So L1, that connects 0, 0 to 3, 2. Okay, and L2, that connects 3, 2 to 0, 4. Okay, so we need to find the equations of those 2 lines. And I do believe that we did a review of the slope-intercept form for the equation of a line. So pause the video and see if you can get the equations for these 2 lines on your own. I will continue without you for now. So okay, that one is easy. It passes through the origin. This one is not. Slope. 4 minus 2 over 0 minus 3. That's negative 2/3. Yeah, it's going in the negative direction. Negative 2/3. Okay, so y minus 4 equals negative 2/3 x minus 0, using the second point for our slope-intercept form. Okay, so y equals 4 minus 2/3 x. Okay, so now we need to find the equations of the 2 planes. Okay, so we said that the upper plane contains A, B, and D. Okay, so this was, but it's still there. This is our point A. This is our B. and this is our C. There you go. And that's our D. All right. So we need ABD. Okay, you know what? Let me copy these points down here because we're going to need them for the lower plane. Okay, ABD. Okay, and the lower plane was ABC. Okay, so let's put that over here. Okay, so once again, pause the video, see if you remember how to find the equation of a plane containing a triangle. Okay, unfortunately, we don't have intercepts this time. So you're going to need to make vectors and take the cross product and plug in a point. Okay, but fortunately for the first one, actually, for both of them, okay, they pass through the origin. Okay, so these are practically the vectors already. You need to find their cross product and then solve for z. Okay, here are my cross products. So the vectors are 0, 4, 0, 3, 2, 5, since we are connecting to the origin. So for x, we get 20 minus 0, 20, y, 0 minus 0, excellent, z, 0 minus 12. Okay, so we can of course use a smaller vector, normal vector. You can scale out by 4, so we can get 5, 0 minus 3. So the equation of the plane becomes 5x minus 3z equals 0. Okay, we're passing through the origin. Okay, so excellent. Z equals 5/3 x. Where did the y go? Okay, the plane is basically parallel to the y-axis. Okay, so any value of y will satisfy these equations. Z equals 5/3 of x. Okay, so same thing over here. We can use the smaller vector that looks like 1, 0, minus 3. Okay, so the equation is 1x minus 3z equals 0. So z is 1/3 x. Okay, almost the same as this one. Okay, excellent. So we have all the information that we need in order to set up our triple integral. I'm sorry, oops, getting ahead of myself. Double integral. Okay, I had a little slip there because something to look forward to. We will do triple integrals not too far into the future. And in that triple integral, that solid that we saw, that's going to be our domain, all of it. Okay, coming soon to a screen near you. All right, so let's set up the double integral. All right, so here's a summary of our computations so far. This is our domain. So it's type 1. X is going from 0 to 3. From L1 with this equation up to L2, this equation. Okay, our upper plane is this, our lower plane is this. All right, and we have a type 1 setup. So here's our template, dx on the outside, dy on the inside. Okay, so we are ready to input our limits. X goes from 0 to 3. Y goes from L1 to L2. So we have 2/3 x in here. I will write that as 2x over 3. Okay, and then up here we have 4 minus 2x over 3. Okay, Excellent. And our integrands are, here is the upper, minus the lower, minus 1/3 x. Okay, so the nice thing is that it simplifies very nicely, but also you don't have y in your function, okay? And I misspoke earlier. It's not that the planes are parallel to the y-axis. They actually go through the y-axis. The y-axis is contained on those planes. I'll show you a little later. Okay, so simplify. We get 5/3 minus 1/3 is 4/3. Integrate. So this becomes 4/3 x, y. Okay, and we're going to need to evaluate. All right, so I snuck in my evaluation bars and lower limit, upper limit, and then we plug them in. And yeah, you know what? We can take the 4/3 all the way out, of course. We should have done that sooner. And then plug in y. So what's going to happen? We will have the upper and then minus the lower, but we have a common factor of x. So we can keep that factored out. So minus 2x over 3. Okay. That might make the algebra a little bit smoother. Okay, so oops, that should have gone. That dy there, we integrated already. And that dy. Okay, so we are back to basic calculus. So what do we have here? These two combine to minus 4/3 x. Okay, oh, check it out. We can factor out another 4. So we have 16. Okay, and that's going to be 1 minus x over 3. Okay, and haha, that was my poo belt. Okay, so we get x minus x squared over 3. Okay, and we are ready to integrate. But to know, we're going to need the evaluation symbol. So let me borrow that here. And there we go. So we will integrate. We will get x squared minus over 2. So let me put fraction in. 1/2 x squared minus 1 over 9 x cubed, I do believe. Okay, so let's see how that looks. All right, so x becomes x squared over 2, x squared becomes x cubed over 3 times another 3, so it's minus 1. Okay, I think that's fine. And then we're going from 0 to 3. Okay, 0 disappears, of course, always convenient when that happens. And then what happens at 3? So x squared becomes 9, so that's 9 over 2. And then 27 over 9 is 3. Okay, so that just becomes 3. Okay, and yes, thank goodness, that is a positive answer. If you got a negative answer, it probably means that you did something backwards. Okay, that's the first thing you should check. Maybe the upper and the lower switched. Most likely that is the cause of the problem. Okay, and what's that? 4.1, that's 3 halves. Oh, cancels with the 3, 16 over 2. We get 8, I do believe. Did I do that right? Yes, we get 8. All right, so that is the volume of that tetrahedron. And yeah, let me show you what I meant about the y-axis. All right, so here is our beautiful tetrahedron. And yeah, see how both of these, okay, are passing through the y-axis. Okay, green is our y-axis. Okay, so that means that any value for y will satisfy our equation, as long as the x and the z satisfy that equation. So is 8 a reasonable answer for the volume of this tetrahedron? I guess so. We don't have the 1,6 ABC formula to help us out, unfortunately, because this is not a right tetrahedron, okay, where the three faces are perpendicular to each other. Three of the faces are perpendicular to each other. All right, so that is our video for today. I hope you enjoy it. And until next time, when I do believe we're going to change the order of integration, I hope you enjoy the rest of your day. Bye.